Good evening, everyone. I am Anish Ambekar, PMRF and PhD candidate from Aerospace Engineering ISC Bengaluru. Welcome to this week's live interaction for the NPTEL course Solid Mechanics. This course is conducted by Professor Ajit Kumar. Today, we'll cover some example problems for the content covered in week 10, which in week 10, Professor Ajit covered theory of beams, which included the Euler-Bernoulli beam, the Timoshenko beam, and also buckling of beams. The first problem is a simple true or false problem. It asks shear center of a cross section must lie within the smallest circle that encloses the cross section completely. So by definition, shear center is the point on the cross section where if a load is applied, where if a transverse load is applied on the beam at that particular point at the shear center, then the beam will only undergo bending and no twisting. So we are asked to, if say suppose we have a beam with some cross section, and the problem essentially says that this is the smallest circle, and we are asked to state that whether the shear center SC will always lie, say, at this particular point 1 or point 2. So point 1 is the point that this statement makes, which is the smallest circle completely enclosing the given cross section. So we'll look at a case of an annular disk with a split. This is your annular disk. Suppose it has a main radius r, and since it's an open cross section, there will be a shear flow from one end to another. It has a small cut here. Let O denote the center. Then from symmetry we know that this cross section is symmetric, and the dotted line that I have drawn, which is nothing but the z-axis. So I'm denoting that axis by EY and EZ. The shear center must lie on this dotted line, which is the line of symmetry of the cross section. Once we work out the mathematics, it turns out that if the radius of this annular cross section with the cut is r, then the shear center will lie at a point which is 2r from the center point. So this distance is 2r, and this point, the point that I'm circling and writing as SC, is the shear center for this particular cross section. Naturally, this is outside of the smallest circle which completely encloses the cross section, which has a radius r from center O. Therefore, this given statement is false. Problem number 2. Shear center must lie on. So would shear center lie on the centroid of the cross section, or the center of mass, or the line of symmetry? As we discussed in the first problem, given a cross section, the shear center must always lie on the line of symmetry if it exists. So for example, if you have like a circular cross section, then it has infinite lines of symmetry which all pass through the center, and therefore your central point O becomes your shear center. If you have something like a flower shape, it has 4 lines of symmetry. All of them again intersect at the same point O, and then this O again becomes your shear center. Problem number 3. Problem number 3. How many lines of symmetry distinct should a cross section have so that we can find the location of the shear center without using analytical method? So suppose I'm just drawing a random cross section. Suppose this is a cross section. As you can see, it has 2 lines of symmetry. Another cross section can be something like the flower one, which we showed earlier. It has four lines of symmetry, right? You could also have like a heart-shaped cross section which only has one line of symmetry. So in the heart-shaped cross section which has only one line of symmetry, you know that the shear center is constrained to be on this line, but you do not know where exactly. But as soon as you have, if you have like if you have a second distinct line of symmetry, then these two lines would intersect, and if they intersect, then the intersection point which lies on both symmetry lines essentially becomes your shear center. So at the bare minimum, you need two distinct lines of symmetry which would intersect and give you your shear center. Problem number Problem number 4. How do we find axial displacement of points in a beam using Euler-Bernoulli theory? So in Euler-Bernoulli theory, if you remember, we start off with our curvature kappa is equal to 1 by r. Is nothing but d2y by dx square upon 1 plus dy by dx square whole raised to 3 by 2. Right? This is your curvature, and from here we make this assumption that dy by dx is basically it's tending to 0. So in this so in this case, no wait, it's asking for axial displacement. So in case of axial displacement, suppose x denotes your initial coordinate, capital X denotes your reference config, and small x denotes your deformed config. In Euler-Bernoulli beam theory, instead of calculating dy by d small x, we actually calculate dy by d capital X with the justification or with the assumption that there is negligible axial displacement. So small x is approximately equal to capital X. This allows us to basically go to dy by d capital X. So for Euler-Bernoulli beam theory, axial displacement is assumed to be negligible. Problem 5. When applying Euler-Bernoulli beam theory, how many boundary conditions do we get for the clamped end of the beam? So this is my beam and it is clamped on the left hand, and suppose I am applying some load P on the right hand. This is your classic cantilever beam problem. And we are using the Euler-Bernoulli beam theory model. So we are asked how many conditions do we have on the clamped end or the left end. So as you can note, in Euler-Bernoulli theory, first of all we only look at the center line. So if you look at the leftmost end, you can see that the center line cannot move up or down. It is clamped. It actually even cannot move front and back. So your y, suppose I write this coordinate as x. So your y of x at x equal to 0 is 0. Similarly, you can see that the center line right here has to on the left hand has to be always normal, because if the center line is not normal to the clamped surface, your cross section of the Euler-Bernoulli beam. So in Euler-Bernoulli beam, your cross section normal is basically along your center line tangent. Since your entire left hand is clamped, it requires your cross section to be along the clamped surface, which would mean that your cross section normal must be perpendicular to the clamped surface. So your cross section normal has to be along the x axis. If your cross section normal is along the x axis, it means that your center line, since it's the Euler-Bernoulli beam theory, your center line is also the direction, the tangent to the center line also needs to be along the x axis, which basically would mean that the first derivative dy by dx at x is equal to 0 is also 0. So essentially you get two conditions, one for displacement, the other for slope. Problem number 6 is a simple true or false statement. The statement which is given is as follows. For a simply supported beam, the moments at the ends where the supports are present are 0. So this is my picture of a simply supported beam, and we are x will vary from 0 to L, and the statement says that the moment m at x is equal to 0 is 0, m at x is equal to L is 0. This is what the statement says. So both of these things are actually true here, because you only have a line force. Like if you think about it along the depth direction, you only have a line of force acting along it. And if you take the moment of that line of action along any point, you would essentially see along a point on the clamped line, you would see the moment necessarily vanishes to 0. So there is no movement coming from the clamp from the simply supported end. And the second part of the statement says that the cross sections do not undergo any rotation. So theta at x is equal to 0 is 0, and theta at x is equal to L is 0. So this is what the statement says. The first part of the statement is correct, moments are 0, but the second part, which is the rotations are restricted to 0, is false. The rotations can be arbitrary, but the moments are 0. No moments are supported in a simply supported beam. So this part is essentially wrong. Therefore, your statement is false. Problem number 7. Which of the following is true? The equation EI kappa equal to m is valid for both Euler-Bernoulli beam theory and Timoshenko beam theory. So for this first statement is true, because we essentially derived this when we were studying beams. We were not studying any particular beam model or any particular beam theory like the Euler-Bernoulli beam theory or the Timoshenko beam theory. This equation EI kappa is equal to m is valid for all beams, for beams, like for beams. So it's valid for both the Euler-Bernoulli beam theory and the Timoshenko beam theory. So the first statement is true. The second statement is center line of the beam undergoes shear in both Euler-Bernoulli beam theory and Timoshenko beam theory. So there is no shearing happening in Euler-Bernoulli beam theory, because in Euler-Bernoulli beam theory, if I draw the center line like this, if I draw the center line, yes, I'll draw it with a different color on top. So if I draw this as the center line, right, my cross section normally is always along the center line tangent. So my cross section is always perpendicular to the center line, and therefore this angle is always restricted to 90 degrees. There is no change in this 90-degree angle, and therefore there is no shearing happening in the Euler-Bernoulli beam theory. So the second statement is false. The third statement is, we use axial force and Young's modulus to find displacement in both the Euler-Bernoulli beam theory and Timoshenko beam theory. As pointed out earlier, we are ignoring both of these beam theories assume work with the assumption that there is no actual, or rather there is negligible actual displacement. So there is no question of finding any actual displacement and any formula for that. So the third statement is also false. So only the first one is correct. EI kappa equal to 1. Problem number 8. When will the results of the Euler-Bernoulli beam theory be closer to those obtained from the Timoshenko beam theory? So in case of both, we obtained, in case of the Euler-Bernoulli beam theory and the Timoshenko beam theory, we obtained a formula for relative error of the Euler-Bernoulli beam theory, and that turned out to be 3 3e by kg into rg by L whole square. This is what it turned out to be, right? This is what we derive from, say, y Euler-Bernoulli beam theory minus y Timoshenko beam theory at like the end of the cantilever with respect to the Timoshenko beam theory. Once we do this, we figure out where RG is nothing but h by root 2. Once we do this, and once we have figured out this relative error, for the results to be closer, we want this relative error to be as less, so as less as possible, so that we represent as less than 1. And if this is the case, here g by L square into 3 by kg less than 1, we just move around the variables to the right hand side and you get L by Rg to be much greater than root of kg by, no wait, L by, sorry, I made a mistake here. So we get L by Rg greater or equal to root of 3 by kg. Once you put g is equal to twice of E upon twice of 1 plus nu, with nu as the Poisson ratio for an isotropic material. This relation turns out to be 6 times 1 plus nu upon kappa for rectangular beams. This essentially means, with correction factor, shear correction factor k is equal to 2 by 3, this essentially means that L by Rg has to be greater or equal to 3.4. So for error to keep on decreasing, you need your beam to get more and more slender. So your results from the Euler-Bernoulli beam theory will be closer to those obtained from the Timoshenko beam theory if your beam is more slender. Problem number 9. This is a simple true or false statement. The same buckling load expression is not valid for all types of boundary conditions of the beam. So, okay. Suppose you have a beam like this and you are applying a load like this. After deformation, so if this is the reference config, so your deformed config would look something like this. Correct? So this is the load that you have. So for this you will get some expression. This is the reference, this is the. However, if you have a different, suppose you have a different boundary condition, suppose like the Clampton. So here we obtained a expression for the buckling load to be something like pi square EI on 4L square. This is for this particular type of boundary condition, but your expression for the buckling load would change if you have like a different boundary condition. So the same buckling load expression is not valid for the same buckling load expression not valid for all types of boundary conditions. Problem number 10. Consider two beams made of same material and having identical cross sections. The length of beam 1 is 10 meter, the length of beam 2 is 20 meter. What is the ratio of critical buckling load for beam 1 and beam 2? So as noted earlier, you have got P critical is equal to pi square EI upon 4L square. Now we are given that they are made up of same material, so E is same, and they have the same identical cross section, so I is same. Therefore, if I take P critical 1 by P critical 2, it would be nothing but L2 square upon L1 square. Like, from simplifying this, you can find this out. Same E and I. In this case, length of beam 1 is 10 meter, length of beam 2 is 20 meter. So you have got 20 square by 10 square. It's nothing but 400 by 100, which is 4 by 1. So the ratio of critical buckling load for beam 1 is to beam 2 is essentially 4 is to 1. Okay. This marks the end of this week's problems that we have. We'll meet again next week at the same time for week 11's content. Thank you for watching this on YouTube. See you in the next class. Thank you.